Uh, Good morning, Professor Pesh.
Oh, good morning. Yes,
How are you?
not too bad. I
Mm.
This morning I think our weather is the same weather as in Mexico City. Uh,
Oh,
it's
mm.
it's very hot here today.
Oh, okay. Yes, here is very hot. Not today, certainly, but hot
It's for many days now, right?
again. Mhm.
Yes,
Yes. Um, yeah.
but
Um,
it's, there's not much we can do, right? We just take it each day. Perhaps tomorrow. I think tomorrow is supposed to be better, but
oh, yeah. When start the to be hotter
usually
in
still 1 month, still
mm,
usually
mm,
July. Um,
mm.
but each year it seems to be uh, hotter earlier in the year.
Oh, okay. Yeah. Mhm.
Yes.
The
So
weather is changing too much.
I think so. Yeah. It
Mhm.
At least it's different than my memory when I was younger. Uh,
Mhm. Mhm.
Maybe I'm.
Just here this year has been unusual
Mm,
hotter the weather. Mhm.
yes.
Mhm.
I have a friend in Florida, uh, uh, near Miami, and he
Oh,
says it's terrible hot.
yes.
They they uh, they expect to get wind from the ocean, uh, but this year not, and it's been 31, or I think today maybe even 34 degrees
Oh,
in Miami this today. So
yeah.
it's very hot for them too.
Mhm.
So uh, I was traveling last week, so unfortunately, my schedule didn't allow me
Mm.
uh, to have our meeting last week. But I I hope that uh, Dr. Sobchak can join us. He I think he was expecting to give some presentation. Is that correct? I think.
Just he said that he was preparing something uh,
Mhm.
about the subject of Clifford algebras and duality.
Yes.
Mm. I was working with that too. I didn't get too much, but I think that I understand better now the how we can avoid the subject
Ah,
because since category theory is not easy to build the approach for
yes. Yeah. I'm always surprised by category theory because it's very abstract, and so the work that you need to do in order to build any one specific construct is perhaps more than you'd expect,
yeah.
more than you would like. But the
Yes.
advantage, of course, is that the formalism uh, insists on uh, a standard, uh, how should I say, maybe a formally correct underlying structure. And from that structure alone, there are many things that you can know must be true without even proof, just because of the nature of the language of category theory. Right? So there are many uh, important, uh, ultimately important structures that are defined by default in category theory. And so the problem often is to find how to apply that structure most efficiently. And
Yes.
it seems, especially the notion of natural transformations is so high level that to understand the application is sometimes difficult.
Yes. But at the same time, I think that is a powerful language because
Yes.
when one get um, to go inside, then I think that the properties of the system is more uh, um, easy to understand.
Yeah. Is forced, is
Mhm.
necessary. It's like there's no choice. You
Mhm.
you must use this method. Um, it it made me well. Your reference to the Levere paper on Grassmann algebra, I read through it again, probably third, maybe fourth time of reading this paper, and
Mhm.
it is surprising what Levere says in just one sentence. You know, he says
Oh,
one sentence, and it could be an entire essay on the subject of Grassmann algebra almost, because the as you say, the language is very powerful. So once you make some specific statement in the language of category theory, it can have uh, very wide implications and deep implications that it might take a long time to work out the details to actually.
yes.
But you know from you know from the formal structure of category theory that it's going to be true, but to understand it is not
Yes.
so easy.
I was working in trying to organize a schedule for going inside the subject of multigrade algebras
Mhm.
in the approach of category theory. I think I had get this organization better now, and I only put some a list of subjects that is needed to cover for that. Then I think that. Maybe we can speak some about this idea.
Mhm.
Many of these subjects was taken from the Laver paper because how you say, he uses many categorical concepts that only present in a strong language, and then it is needed to work around these concepts that
Yes, yes. To
he
understand
presents.
the
Mm,
implication of the
mm,
definitions and so forth is
yeah.
not
Mm,
not so straightforward. But yes, I think so. your approach is more general than just Grassmann algebra, or and you see Clifford algebra as in the context of multilinear algebra. Sorry, I guess. So you cover not only category theory, but Grassmann algebras and symmetric algebras.
Yes, but maybe I can. I don't know if we need to wait more, or maybe we can start.
Yeah, I think yeah, if you'd like to, I'm very interested.
Mhm.
Uh,
I'm going to show to you one um, uh, a draft that I was um, uh, I have been working and okay. Okay. Um, oh, here it is. Um,
yes, I see it.
okay. Then this is the title that I had select for this. Maybe later we can change or something. But the idea is to start with an introduction where I am putting the principal concepts or um, uh,
But you start only with commutative algebras.
yes, because the multigrade algebra is commutative algebra. Is put in the in the approach of abelian categories. Then for this, I have been working with that. And the concept of tensor categories and multigrade algebras are in the approach of abelian categories. For that, I had been I started with the uh, with the subject of uh,
So so you start with this as an example of the graded structure, I guess. But ultimately, will you make it more general? Is that do you?
no, I don't.
Maybe I'm confused about the application to Grassmann algebras and to Clifford algebras.
Yes, but I don't know where is the um, because your yes, your question or your point is that why we are only to speak about uh, um, associative algebras, or I don't
No,
understand.
yes, associative is okay, but if you have commutative algebras, then then you rule out uh, direct application to Grassmann algebra and to Clifford algebra, since
But
it's
not
not commutative, right?
not commutative. But I was looking for the if it's, here I am speaking about the commutative algebras, or
Yes, at the title, I think. Yeah.
okay, yeah, at the title. Then the duality concept in category of okay, here yes, commutative graded algebra. This is quite because in the Laver paper, he speak about commutative graded algebras. I remember I take this the name from that. Uh, but I think that he is using the concept, the idea of commutative in a general approach of his language, including that when we have a product and then we invert the order of the product, then we get one minus to the power
Ah,
p,
okay.
where it is
Yes.
the degree of the of the algebra, and sorry, of the first
Okay.
element is the product.
Yes. So
Uh,
the what we would call the non-commutativity is absorbed into the concept of grade, right?
Yes,
So,
yes,
uh,
this is the idea. And for that, I only take the name from the Laver papers in this in the same idea here.
maybe perhaps it's Lever's fault, but I would say in English at least it would have been better to say category of graded commutative algebras. So to put the word graded first, right? Uh,
Graded commutative algebras.
to
Okay.
to
Mm,
me that I understand that more clearly, right? Is
yes.
that it's only commutative in conjunction with the notion of the grade.
Yeah.
Uh,
Okay. Then maybe if you permit that, I can change immediately
sure, no problem. Yes.
this here um, category of mm, graded commutative. Yeah, and then I move from here.
Yes.
Uh, Okay. And then,
Now I'm happy.
okay. Uh, thank you, sir. No, I think it was
Yes.
because the okay now because some put some uh, um, open some windows and then is a problem for
Oh, it's
uh,
not updated.
this. Okay, now mhm,
Yes.
okay. Then okay, then we started with this with the review of some important concepts in um, category theory that are needed for the building of exterior algebras. Then I started with the concept of duality, and here uh, I am only putting the uh, principal ideas referred to the module category, and then using this category for define the properties of the duality. Then here I am using two functors F and G between two module categories, MC and MD, and then we can conclude that there exists a natural isomorphism that is called here eta and zeta for the product of these two functors that give to us the unit, and in fact this is co-unit. Then this is based in the concept of duality and in the concept of adjunction of um, adjunction operation in category theory. Then this is the first important ideas that we can that I am putting here. Uh, okay, and then based on this property, I speak about the Morita and duality that is defined in terms of two functors. One, no, both are contravariant functors here, and then with those we can build a property that is called the Morita duality, because if we use a module that are reflexive module, that is his left and right module, then we can define the associate with each module one operations that we are going to call the dual of these modules. Then I think that this kind of of definition of duality is the definition that we need for about this problem. By the way, here I am not putting the detail of the definition of duality because I am adding an appendix at the end of this draft that give the common definition of duality.
Mm. Some common examples might be good too, such as in multilinear algebra, but of course you're going to go to in more detail, but still to show the application of this Morita duality to something that we already know.
Yeah. But the idea of application of duality in multilinear algebra is not here because I am waiting for the definition of a tensor category.
Yes,
And
yes, I
then
see.
when I define the tensor category, I get to
Mhm.
bifunctors that are the tensor product and the bilinear functor. And then
But
this is this includes the properties of duality in bilinear products of standard algebra.
it's I guess here in your section 1.1, um, it's before the definition of grade. You're dealing only with the notion of duality, right? Um, and so an example might be just ordinary linear algebra, um, where we don't need the concept of grade. We have just
Uh-huh.
so we it'd be nice to show that Morita, you know, a duality is the same as duality in linear algebra. Um,
Yes, but uh, here I am using this the duality without the reference to any particular category, but not because I am using here the modules categories, and then for this module category, I am building these properties, and then I get
at, at the level of a ring, right? So
yes. Uh-huh.
as long as the structure is a ring, then this definition is sufficient.
Yes. But maybe you are suggest that we can add some examples of duality here in the introduction.
Yes, it is just the first trivial example of linear algebra and how how each of these functors, what does it look like in this very simple case?
Yes. Okay. Uh,
But it's okay. Uh,
okay. Then
this is exercise for the reader.
maybe we can put that, but I have been uh, finding many problems for defining the more elementary examples of that we used to use in mathematics in terms of category theory, because at the end there are uh, conversion quantity of properties that are behind these ordinary definitions. Then this is part of my conflicts here because some elementary examples are at the end too much complex because they
Yes.
requires many definition of properties. Huh?
Yes.
Then okay, but I am going to look for the way of introducing here some of these examples. Mhm. Okay.
Yes.
Okay.
Something just a little bit more constructive, so that you when you read it first, you think, oh, yes, it's like this, but more general. You know.
Okay. 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 Then after of this. We I started with the definition of an abelian category. Then an abelian category requires the definition of a byproduct. Then I like this definition too much because I think that these properties related with the definition of this product is related with the formulas that Professor Garrett are using.
Yes. Yes, it looks very much like that.
Yes. And then, of course, a first definition, I don't know if I am going to add here this, but at first definition only is established using only three um, 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 three objects in the category. Then two objects are the elements of the product, and the third are the product. Then I can put out the index here, and is in practice the definition of the product. Uh, and and then with this definition, then this equation is more simple, only using these two terms here, and then I can define the product in this way. But I think that this generalization of the product of the byproduct is better for the definition later of Clifford algebras. Then, in this way, I think that it is important um, to put here this. Um,
Just a moment. I
Yes.
need to do something else here for a minute.
I called Larry's. You were nowhere in the schedule. Nowhere. Whoever you spoke with, and it was not the lady who works there. So she has booked you now for sure on the 19th, Wednesday, which is a day that I believe you have a meeting.
Oh,
Maybe.
okay, I can reorganize that.
Okay, so you don't have to rush.
Okay. What the heck?
I don't know.
They lost the booking.
Well, it was one of the guys, right?
Yes, it was. Wasn't her.
No, it was one of the guys, and it wasn't Larry. Somebody did it and didn't write it down. Maybe they put it in the wrong month.
Okay.
Okay,
Thanks, sir.
you're safe. I can practice.
Okay. Oh, anyway, okay, that's good.
Okay. Then okay, then here there are some definitions that are required later, and not only that, but give to us some important properties. First, we define an additive category based in the definition of this by product, and then an additive category have a bifunctor that is this circle plus and acting on the category, and then we get the direct sum of elements of objects in the category, and not only on the objects, but then the morphemes are added in the same way. Then for objects in the category, then I suppose that there exists an object Y that is called the direct sum of these two objects, and this is wielded with the direct sum of the objects in the category. Then the this operation applied to the category is only the sum of all the objects in the category. And for the arrows, we have this property that I think that it is too much interesting, because P here are representing projectors, and I is represented inclusions. Then here we have that a project applied in the target in the target object in product with the direct sum of two morphemes is sended to the corresponding morphemes in the original object that in composition with the projector that is giving to me the original object. Then these operations are the representation of the properties of this direct sum bifunctor. And a similar situation is getting for the direct sum bifunctor, and with the inclusion morphemes in the category, then this property are related with the functor that is the Cartesian product of these two objects and the coproduct of these two objects in the category, in the B category. Then
what is the meaning of the prime on the character P prime or character I prime?
Yes, here is the meaning. If I take in the category C, that is the first element here in the direct sum, then F1 is a morphism between two objects in the first element of this direct sum in the B category. Then A prime is the target or the target of all in the codomain of the morphemes F1. This is A prime. Here, B prime is the codomain of the morphemes F2.
Yes, but in the next
here,
one, yes,
then
you have the prime.
Yes, this prime is if I think that is needed to write something, but I can say it in this way. When we build this product, sorry, maybe I can put this here because we have this relation between objects AG and AK. And then if we build a similar sequence to this here, I can put here AJ prime and AK prime here. And then the inclusion morphemes is I prime J and P prime K. And then between these two objects here, I have the F1 morphemes, and here we have the F2 morphemes. Then I am including in this product here the inclusion and projection of two objects, of different objects that are part of the product. Then this is the meaning of the prime in
Yes,
the.
I think I see. Yes.
Okay, yeah. Mhm. Okay.
So this is the universal property that you wish to emphasize for this.
Yes, here is uh, and this is a natural isomorphism. Then this means that there is a natural transformation in this product. And then after I introduce here the definition of an additive functor, then an additive functor is a functor in the between two categories that transforms the addition of two morphemes in the A category with the addition of two morphemes in the B category, with the corresponding addition of the functors in the B category. Then this is in the definition of additive functors. And then with this definition, I can start the definition of exact functors that are related with the building of exact sequence. I think that I am defining after the exact sequence. It is needed to define before here, but with that definition of an exact sequence, here I can define an exact functor. Then a sequence is exact when the kernel of the kernel of B is equal to the image of A. In these terms, this is exact. Okay, no, sorry for the comment. And then I insist I need to put the detailed definition of exact sequence here, and I think that it is later in this draft. But here it is important that for one exact sequence of objects in a category A, then I can get with the functor T and left exact sequence or right exact sequence. Our right exact sequence start with TA then follows with the TV. Sorry, no, with the right exact sequence. Start with 0 here, and then after TC, TB, and TA, and then ends in TA. Then we can have a left and right sequence with the application of a functor. And in this case, we say that the functor is left exact or right exact in those cases. And when those and when the functor are right is exact and left exact, we only say that the functor is exact. But it depends of the properties of the functor T. Then with the properties, we are now to the definition of a chain complex that is that the complex that Lavers use in his paper. Then here is defined a chain complex that is defined in an abelian category, and it is defined using linear transformations of the objects in the category. Then when we can define this linear transformation between objects in the category, we say that we are building a chain complex. The properties between the for the composition of these elements of the linear transformation between the objects are this, that it is important because these properties are related with the characteristics of the complex of the chain complex. Then for this chain complex, it is defined in a more general case. The exactness of this sequence by the homology objects that are wielded with the quotient of the kernel and image of the linear transformations in this complex chain. Then
very complicated.
Excuse me?
I said it's a very complicated definition.
Yes, it is very, but I think that we need to go inside of this definition, because when I was looking for the definition of causal complex that are used by Laver, I found higher complications in the definition of this. Then I think that we need some homological concepts that are needed for this building. I found some of the papers related with the causal complex that is based on uh, different kinds of definition of algebras that later maybe we are going to need in the study of the properties of the graded algebras. Then this is the principal properties. I'm going to pass for, this section, and I immediately come back, but only for speak about the schedule that I say to you. Here is as list of concept used in the module category. And then, okay, here is the definition of the exactness. And here, finally, are the another concept that are needed. Okay, here additive functors maybe is needed to review some more properties of them, and another properties of abelian category. But here there are some subjects that is needed to avoid, because are required here, and then are the tensor product and bilinear forms, and of course the more discussion about the exact sequence and complex. Then about these concepts, I have not added nothing here in this draft. Okay, then I go back here to some properties of the module category. And in the same way, I have only a list of properties without almost any discussion. Then first here the definition of a left R module, and then is is a map from a ring R to the left endomorphism of M. And M is a module in the of this ring R. Then this is the definition of the left R module, and the properties of this are listed here. Lambda is a a map acting on the module by the left, and then we get this property for elements of the ring and elements of the module. This is the standard definition of a left module, but after I have here the home set of a ring that are wielded with the two modules M and N. Then for this home set have the property that it's an abelian group. Then for two modules, okay, for the two modules, okay, here is only the presentation of this, the property that this is an abelian group. Then, okay. Here only is presented this this definition, and here is the definition of the module category. Then in the module category, we have the objects that are sorry, the objects in the category. Sorry for the notation, because I am mixing here the notation. I need to clean this because I am using this calligraph character for representing a category. And then here I need to interchange this notation. Okay, but here we have the objects of the category. Here is this is the object set, and this is the home set of the category and the composition operation. With these three elements, I define the category of modules, and then the elements of the home set are a transformation of I take two objects in the category, and then I form the home set of these these objects in the category. And then with this, it can be seen that this category have the property of be an abelian category, because we have in this operation the properties of an abelian group. Then here is the definition of the module category, and then I define the functors in the module category. Then for M and N are modules, the set are Mn is an abelian group. And then I define, this was made before the definition of an additive functor, and only I repeat here that definition. Okay, another property in here is that if we define an homomorphism between two rings, then this morphism phi induce an R module structure between the left S modules, because for every homomorphism F from M to N, it can be possible to define an R homomorphism with these properties. Then we can see that this is an R module, and left R module in the category. With this property, okay, with this definition, we can see some other properties, because we can define an R isomorphism that is applied in the module, and this define an relation between the ring and the module, and then this give to Oms and left R module that is defined with this property. Then for okay, and in a similar way, I have here the definition for AB by module, and then we have an RS isomorphism. We have here two rings, R and S, that are related with this property. And then looking about the properties of these isomorphisms, we can find that this is the base for the definition of a natural transformation. Then, if we take an element E of the ring that is a non-zero idempotent, then we can build a bimodule with the product of this element of the of this idempotent element of the ring. Then we can define in the same way a left module that is is defined here, and this left module is a subgroup of M, and okay, and here is mm,
some of these definitions that they are all internal definitions, and so it takes some time to appreciate, because
yes, I
to think
thought
of examples is not so easy.
Yes, I think that it is needed. How I said before, I have here only a list of concepts that I find necessary for will the required environment for the uh, multigrade algebras. Then this is because here I am only presenting some list of concepts without more uh, discussion. Yes. Mhm. Okay. Maybe it is too much preliminary draft, but maybe I can send to you a copy of this, and in this way, I think that we can work in a better way with those. Mhm.
Okay, so the next major section is the definition of evaluation.
Yes. And here I only put the definition of evaluation that Professor Osiewicz used to use in his paper of um, 350 años o controversias de fundamentos de cálculo diferencial e integral. In this paper, he defined the evaluation, but in category theory, there are more extended definition of evaluation that I am planning to include here and discuss with this definition that Professor Osiewicz used to use. Uh, then because the idea is that we have the definition of functors that are part of the functor category, and then these functors are related with the evaluation concept. Then
But
I think
if you have the same level of description as in the previous section, here I think you must talk about Cartesian categories or something
yes.
like this, such that we have this exponentiation.
Yes, I think that we need to use this approach. Yes. Mhm. Yeah.
And that this here it is assumed that we understand this notion already of an exponential object, right? That
Yes.
presented in the context of set theory or or
Okay. Then I don't remember if I included some of this concept in the appendix, but of course I need to add this uh, 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 to add this concept in some part of this paper. Okay, here I only are the section that we was discussed before, and that are taken from the Laver paper. Mm. And okay, here is the definition of the Kosul complex, and then I added some definition of complex here. Sorry, I need to organize it in a better way because it is uh, presented before. Mhm. And for Clifford algebra, I have not too much. Then I need to put more detail. And then here are the standard definition of the concepts of category theory. Mm. And then, okay, then, I define, uh, I added an appendix with the concept of monads and algebras. And then here there are some of the properties. Uh, okay, here is the direct sum of modules that maybe is needed to add uh, in the body of the document. And okay, and here is a description of the causal complex. And okay, yeah, and the reference that I am using here. Mhm. Okay, then this is in general the ideas that I was working with this.
As I said at the beginning, when you read Lever's paper, you think, wow, this is like an exercise to understand a very large number of concepts in category theory to make a simple statement in the end, right? So
Yes.
so once you understand each of these prior concepts, then the statement of Grassmann algebra is relatively simple. Right? It's just an application of some very high level concepts in category theory. But it's difficult, I think, to make a connection with the approach of Dr. Sobczak. Although here you did have one reference here.
Sorry,
It's okay.
like I put the reference?
No, well, I would like if you could show me again the section where you dealt with the
Yes.
role of the projectors. What I was saying is that there is a lot of category theory, but not an easy connection to Dr. Sobczak's work. But you had one section which you showed. Yes, here.
Here before?
No, where you a little bit before this. Yes. Yeah, here at no, you went too far. I think 1.3 perhaps.
Oh, okay. 1.3?
So yes.
In the definition of additive categories?
At the line at the very top of this page.
Oh.
Can you here? Yes.
Oh, okay.
So this is an example that here you're defining byproduct as an essential part of the definition of abelian category. So this construction of in terms of I and P is it is an internal definition of the form that is used by Dr. Sobczak. That's so it means that this construction of byproduct is completely general, right? It's something that can be constructed in any abelian category. So any category in which we can define the sum. So I think here would be a good place to try to produce some examples that and to show how these morphisms, the I and P morphisms, can be expressed. For example, in Dr. Sobczak's case, it would be expressed in terms of the algebra of in terms of matrix algebra, for example, where the objects are matrices and
and the idea is to use this kind of general definitions and relate with the or associate with the standard definition of.
Yes, as an example, or we might say as a representation of this
Mhm.
internal structure.
Okay.
But
Mhm.
the quote that you have here is important, right? The description is internal, which means it doesn't de depend on any notion outside of the category itself. To understand this better.
Okay. Okay. Then
Yes, I think focusing on this definition of byproduct seems important to me to establish the how is this related to what Dr. Sobchak is presenting in uh,
yes, I think that we can extend this or not extend, but emphasize this definition with studying some of the properties, because uh, when this is defined, and this is, I had taken this from the reference 7, and I don't remember what is that, but here is the page, and here there appears a detailed discussion when is used only two objects that are the factors in the product, and a third object that is the product. Then I think that this approach can be interested, and maybe this can help to us to associate it with the ideas of Professor Garrett. And
yes, in
after,
particular, Professor Garrett, Professor Sobchak is very interested in the notion that there exists what he called local duality. But I would make tentative analogy that to say that uh, local for Dr. Sobchak is the same thing as internal here.
okay,
Um,
okay, yeah,
uh,
I understand that.
and what we had described as global duality is the same thing as external.
Okay. I say. Mhm.
Because I also struggle for some time to understand how we can have this duality uh, in the local sense, right? Uh, how can it be that within one Grassmann algebra we can build uh, something dual when we have only one Grassmann algebra? And here, maybe this is a part of the answer for this, because this Grassmann algebra is abelian, and because of that, we can always make this construction of a byproduct. But now the difficult thing is to understand this as a kind of duality. So you have the definition of dual right at the beginning, right? At the
Yes.
beginning of your
Yes. Oh, here it is. Mhm.
It's just prior.
Uh, But I am using this definition in terms of rings, and uh, mm, but there is a more general definition of Morita's duality. I think that in general for two functors F and G that are adjuncts, he defined the concept of duality. Then here is used for define the concept of duality in terms of rings and modules. But for in general, for a category, we can make a similar definition. Mm. And but I understand that your idea is to look for the definition of an internal property and an external property. Here, internal is in terms of objects in the category. Then this expression is defined in terms of objects in the category. And when they say external, they are referring to relation between categories in general. No? And I think that the this is the forms that they use here, the terms internal and external. Mhm.
Okay. Can you show me this reference 7? I'd
Yes.
like to see.
Mhm.
Oh, this is Sanders.
Oh,
Okay, yes.
MacLean, Sanders MacLean.
Standard definition, yes. Okay.
Mhm.
Okay, I will look at that.
Okay.
But if you when you are ready, if you can send to me this draft, it would be helpful, I think, or useful.
Yes. If you have not a problem, I can send it like it is now.
Okay.
And maybe when I get working more, I can send to you a different version of this. Mhm.
Okay, sure. It's good.
Okay.
All right.
Mhm.
So today we have only our discussion. Uh, if we can keep this our normal schedule, it would mean that in 2 weeks we would meet to return to our normal scheduled meetings.
Okay.
I will send an email to Dr. Subject to confirm that he would be possible for him to give a presentation in 2 weeks.
Okay.
And then we return to our every 3 week schedule. In 2 weeks is let me see. 2 weeks is 19.
2 weeks.
Oh, yes.
2 weeks
Perhaps I
is
have,
19.
yes. Perhaps I have conflict with that. I have to check.
Okay.
So if not 2 weeks, then we will make again 3 weeks from today. It would be 26 then.
Yes. Not problem for me. Mhm.
Okay, I will let you know of the schedule that is best for Dr. Subject to continue his presentation.
Okay.
All right. Thank you very much, Jesus. That was
Thank you very much, Professor Fish. And we see in 2 or 3 weeks.
yes. As
Okay.
I think it's some good progress to get towards this connection between the two concepts, between the categorical presentation of the ideas that Dr. Subject has introduced. I think it's very good. Okay, I
Okay.
will see you in 2 or 3 weeks time again.
Okay. Okay.
Bye for now.
Okay. Mhm.